So here now we want to find the gradient of the function at the point P. The coordinate point P are 2, minus 3 and 1. So the gradient of the function at the point 2, minus 3 and 1 is equal to x equal to 2, where minus 2 into 4 is 8i. Then z cube z is 1, so is equal to 1j. Then here y is z squared, z is 1, y is minus 3 into 3 is minus 9, minus 9k. So is a vector that is minus 8i plus j and minus 9k, that is the gradient of the function at point 2, minus 3 and 1. So I am going to give you the example for finding the directional derivative of the function, that is fxyz is equal to x squared plus 3yz and plus 4xy. So this is my given function, and the point is 1, 0, minus 5, and the direction of the vector a is 2i minus 3j plus k. So we write the formula for the directional derivative. That's equal to gradient of the function at the point x, y, z dot unit vector u. So our gradient of the function is f of x I plus f of yj plus f of zk. Find f of x. My x is changing, yz is constant. I get here 2x plus 4y I. Then with respect to y, we differentiate, we get here 3z plus 4xj. And with respect to z, we get 3yk. So this is at any point x, y, and z. We can just rewrite this one. This is my gradient of the function at the point, gradient of the function at the point x, y, and z. Now I find the gradient of the function at the point, given point P. My point P is 1, 0, and minus 5. My x equal to 1, y equal to 0, I get here 2i. My x equal to 1, y equal to 0, z equal to minus 5. So get here minus 15 plus 4j. Then y equal to 0, this is 0k. I simplify this one, I get it 2i. And here this is my gradient of the function. Next in my formula, I need the unit vector. For that one, I need the magnitude of the vector. Magnitude of vector A is equal to 4 plus 9 plus 1 in the root. And this here u1 square, u2 square, u3 square, and that is equal to 14 under the root. So my vector u is vector A over magnitude of vector A. So that give me here 2 over root of 14 I minus 3 over root of 14 j plus 1 over root of 14 k. So this is my u. And now I can take here the formula, that's my dot product, the gradient, the directional derivative of the function at the point 1, 0, minus 5, and direction of u is equal to gradient of the function at the point 1, 0, minus 5. Dot product is u. So I have these two vectors. I am having here the vector here is 2, minus 11, and 0. This is my gradient. And dot product is u. My u is 2 over 14 under the root, and minus 3 over 14 under the root. I am having here 1 over 14 under the root. I take the dot product of these two vectors, that give me 4 over 14 under the root, and minus plus get 33 over 14 under the root plus 0 over 14 the root. Simplify this one. We are having here 37 over 14 under the root. That's my directional derivative of the function at the given point. Another example, we want to find the directional derivative of the function f x, y, z. Here is equal to sine yz plus ln of x squared. At the point P, there is 1, 1, and pi. So in direction of the vector A, that's equal to I plus j minus k. So again, we find the gradient, then find the gradient at the given point, and then we find the unit vector, and we take the dot product. So the formula for this one is, we want to find the directional derivative of the function at the point 1, 1, and pi. This means we'll find here the derivative of the function at the point 1, 1, pi, and then we have we write here the general formula. We write here the gradient of the function, and then we have the gradient of the function at the point 1, 1, and pi, dot product the unit vector u. So I find the gradient, and then we proceed further. To find the gradient, I have here the gradient of the function at the point x, y, and z. This is equal to f of x I plus f of y j plus f of z k. What's my f of x? I have y and z constant. Ln of x square is 1 upon x square into derivative of x square is 2x I plus f of y. We're having here ln of x squared, there will be 0, y is changing. We get here sine yz into derivative respect to y. We get here z into j plus we are having respect to z, that we get here cosine yz and derivative respect to z is y into k. So this is my gradient. I find the value of the gradient, and you must remember that cosine pi is equal to -1. So use this one and we write the value of the gradient of the function at the point 1, 1 and pi. So that give me here 1 upon x, this 1 upon 1 I plus z equal to pi, then here cosine pi, and because here y equal to 1 plus y is equal to 1, we have cosine pi k. So as I mentioned that the value of cosine pi is equal to -1, and we use here the value of cosine pi is equal to -1. So get here the gradient value, gradient of the function at the point 1, 1 and pi is equal to I minus pi j minus k, because the value of cosine pi is equal to -1. We find here unit vector. We are having a vector A is equal to I plus j minus k. The magnitude of vector A is equal to 1 plus 1 plus 1. Under root we get here root of 3. Then I can write my unit vector u is equal to A or magnitude of A, that's equal to 1 over upon root of 3I plus 1 upon root of 3j minus 1 upon root of 3k. So that's my here unit vector. Now I can write my directional derivative of the function at the point 1, 1 and pi is equal to gradient of the function. Gradient of the function is I minus pi j minus k dot product with 1 over root of 3I plus 1 upon root of 3j minus 1 upon root of 3k. We know the formula for the dot product. We use the formula. So we get here 1 upon root of 3 minus pi upon root of 3 minus 1 upon root of 3. So 1 upon root of 3 minus become plus. I get here 2 upon root of 3 minus pi upon root of 3. I write here minus 2 pi over root of 3. That's my gradient of the function. We're having more example. We want to find the directional derivative of the function x, y, z and the sine yz plus ln of x squared at the point 1, 1 and pi. In direction of the vector A, that is equal to I plus j minus k. Now as we know that we find the gradient of the function at the point 1, 1 and pi and find the unit vector, and we take the dot product of these two. So first we find the gradient and then we find the unit vector and the dot product. Find the gradient with the formula gradient of f x y z is f of x I plus f of y j plus f of z k. And now find f of x is equal to 1 upon x squared, then derivative of x squared is 2x. So we simplify this one, we get here 2 upon x I, then plus we're having the derivative here, the x is constant and we have sine yz. So we take the derivative, we get here yz, sine we have cosine yz, and derivative yz is equal to z respect to y. Then we have is j, and then we having with k. Again this z, this is sine x squared is a constant, and sine yz, take derivative, we have cosine yz, and then respect to z is y. So this is my here, I can just simplify this 2 upon x I plus z cosine yz j plus y cosine z k. Now we substitute the values, x is equal to 1, y equal to 1, z equal to pi, then cosine pi is equal to -1. Substitute here, we get here this 1 upon 2i minus 2i plus pi cosine pi j and cosine pi k. Cosine pi is 1, we get here 2i, and we are having minus pi j minus k. Now we use here this part 1 of the solution, and now we're going to get the unit vector. A is given is called I plus j minus k. Then magnitude of A is 1 plus 1 into root of 3. And then we have the u is equal to divide by root of 3. We get 1 upon root of 3 plus 1 upon root of 3 minus 1 upon root of 3. Now we take here the dot product of this two. We get here 2i minus pi j minus k. And we take the dot product of this one. We get here 2i into 1 upon 3i. We get here this equal to 2 upon root of 3 minus pi upon root of 3 plus 1. And then here we get here minus 3 upon root of, we're having here 3 upon root of 3. So we take root of 3 common and we can get here the value of the directional derivative is equal to 3 minus pi over root of 3. So that's how we can find, we say, a directional derivative of the function at the point 1, 1 and pi in this unit vector u is equal to 3 minus pi over root of 3. So that's the solution of our problem. We have application of some properties of the gradient that I want to mention. Number one is that we have a function of xy, it's a differentiable function, and if the gradient of this one is 0, then we say the gradient, the directional derivative of the function is also equal to 0 in other direction for r values of u. The second is that the maximum value of the directional derivative of the function at the point xy in direction of u, the same as we say the maximum rate of change, is given by the magnitude of the gradient, and it occurs in the direction of the gradient. So the magnitude, the maximum value is the magnitude of the gradient, and the direction is the direction of the gradient. That's the second point. Then we have the maximum value of the directional derivative that's given by minus magnitude of the gradient. And we want to find the direction, the maximum rate of increase, or this is minimum rate of increase or maximum rate of decrease that occurs in the direction of minus gradient. So that's very important concepts which are being developed with the gradient, that the maximum rate of increase is the positive value of the gradient and maximum rate of decrease is negative value of the gradient. And direction is also, for maximum rate of increase is positive and minimum rate of decrease is negative. So these are the points. So when we say the rate of change with respect to in direction of u will be our directional derivative. I put as a note.